This is for STA2023 Statistical Methods, Chapter 8, Video 4. We're going to do another example, as in the previous video. We're doing a two-proportion z-test. So in the fall of 2004, the drug manufacturer Merck Pharmaceutical withdrew Vioxx, the drug that had been used for arthritis pain, from the market after a study revealed that its use was associated with increased risk of heart attack. The experiment was placebo-controlled, randomized, and double-blind. Out of 1287 people taking Vioxx, there were 45 heart attacks, and out of the 1299 taking the placebo, there were 25 heart attacks. According to Los Angeles Times, October 23, 2004. Perform a hypothesis test to see whether those who took Vioxx had a greater rate of heart attack than those taking a placebo at a level of significance of 0.01. So we have two groups. The two groups are Vioxx and placebo. The Vioxx group had 45 heart attacks, that's what we're measuring, out of 1287, which is 0.035. The placebo group had 25 heart attacks out of 1299. Notice the ends are different, and that's okay. As long as they're similar. If they're really different, I would worry if the one end was really small, but in this case they're fine. And that's 0.019. So the question is, was there a difference between the Vioxx group and the placebo group? Is there a greater chance of heart attack in the Vioxx group? So our HO sets the two groups equal to each other. The proportion of people in the Vioxx group who had heart attacks is equal to the proportion of people in the placebo group who had heart attacks. PV equals PP. And then PV is greater than PP. The proportion of people in Vioxx group who had heart attacks is greater than the proportion of people in the placebo group who had heart attacks. So again, before we move on, 3.5%, 1.9%. Do you think there's a difference saying that there's more people having a heart attack in this group? That's what we're looking at. So we check our conditions. N1 times P1, 1287 times 0.035 is 45, greater than or equal to 10. 1287, 1 minus 0.035 is 1242, definitely greater than or equal to 10. The other group, other N, 1299 times 0.019 is 25, that's greater than or equal to 10. And 1299 times 1 minus 0.019 is 1274, which is greater than or equal to 10. Two groups are random, independent within the sample, and the null hypothesis is assumed to be true. Now again, we're going to use the combined p-hat, so we add the numerators, 70, the denominators, even though they're different, 2586. 70 divided by 2586 is 0.027. That's the p-hat we're going to use for our SE. Be very careful typing this in the calculator. Square root of 0.027, parenthesis 1 minus 0.027, close parenthesis, 1 over 1287 plus 1 over 1299, following the formula. You should get 0.0064. Be careful, 0.0064. To find your z, it's the first group, 0.035, minus the second group, 0.019, divided by 0.0064. You should get a z of 2.5. So again, practice with your calculator. 2.50 would actually be way down here, and we're looking for greater than, so it's a very small p-value. When you look up 2.50 in the table, you get 0.9938, but that's less than. We're looking for more than. So 100 minus 99.38 gives us 0.62%. 0.62% is 0.0062. Remember, that's the decimal, that's the percent. Be very careful. To go from percent to decimal, you move it over 2 to the left. Be careful. So our alpha is 0.01 and p-value is 0.0062 compared to 0.01. Before we move on, we'll check it on the calculator. In the calculator, we go to stat test number 6, two proportion z-test. Remember, the calculator wants the two fractions. It does not want the percents. So we're going to put those two fractions in here. So it's 45 out of 1287. First group, first fraction. 25 out of 1299. And we're saying that the first group is greater than. When I go to draw, again, if you get an error at this page, one of your plots is probably on, 2.46. And again, we did it by hand. We got 2.50, very close. Remember, the calculator is going to be more exact, but they're very close. We got 0.0062. They got 0.0069. Very close. So again, be careful with your decimals, but the p-value is definitely smaller than alpha. When your p-value is smaller than alpha, we reject HO. there is statistically significant evidence to reject HO because of a very small p-value, we conclude the proportion of people on Vioxx who had heart attacks is greater than the proportion of people on placebo who had heart attacks. So what we're saying is, if you take Vioxx, you have a higher chance of a heart attack. Higher chance of a heart attack. So when we do our confidence interval, remember, it's the first p hat minus the second p hat, plus or minus your Z star times your SE, and because we're doing 99%, we're doing 99% now because of 1% alpha. Our Z star is 2.58. We learned that in the previous chapter. Times our SE, 0.0064. We get negative 0.0005 and 0.0325. Now please understand something. We said that it is a higher chance of having a heart attack. So if it's higher, I'd expect 2 positives. If it was lower, I'd expect 2 negatives. If I wasn't sure, probably a negative or a positive. In this case, we got a negative and a positive, but we're supposed to get 2 positives. But let's back up a second. This negative is very, 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 very small. 0.0005, so it's right on the edge of being 0. So we're just going to go ahead and call it 0 because it says greater. So we are 99% confident the proportion of people on Vioxx who had a heart attack is between 0% to 3.25% higher. Remember, we're interpreting what the positive means, higher than the proportion of people in the placebo group who had heart attacks. So what's important is we're saying that if you take Vioxx, it's greater. So we're expecting 2 positives. It's greater, but not by much. And this is where you really get to think and use the statistics, saying that, let's say this Vioxx drug really helped you and it cured whatever ailment you had, but there's a risk, 0 to 3%. But if it really helped you, would you take that risk, 0 to 3? But if it was 75% to 90% increase in having a heart attack, you probably wouldn't. But 0 to 3, there's the data. So yes, it's greater, but by how much is also really important. And again, all of your calculator steps, follow your calculator steps from the previous problem. And then to finish off the chapter, understanding hypothesis testing. If the conditions fail to be met for the hypothesis test, the Z statistic will not follow a normal distribution. That's why we always do the conditions, to make sure everything passes, so we can assume it's normal, so we can do a Z. This means we cannot find the p-value using the normal curve. There are other methods. So some issues would be if your sample size is too small, if your samples are not independent, or if your samples are not random, they would break the conditions. So we want to make sure we pass the conditions to do a Z test. But you'll notice that there's some things called a type 1 error or type 2 error, and I have some graphics, and I think this one explains it the best. So here's the idea. If you reject HO, it's because HO is false. You reject it. It's false. That's a good rejection. Correct. Good job. But if you reject HO when HO is true, you made a mistake. And the name for that mistake is a type 1 error. So we have names for the mistakes we make. So again, if you reject HO, that's because HO is false. Correct. But if you reject HO when it was true, you made a type 1 error. If you fail to reject or do not reject, it's because HO is true. Correct decision. But if you do not reject or fail to reject HO when HO is false, you made a mistake. That's called the type 2 error. So if we make mistakes with our conclusions, we have names from type 1 error, type 2 error. Okay? And that concludes chapter 8.